All right. Welcome all. Uh, Let me remind you what we were doing last time. We started metric spaces. Metric on a set x is just a function, right, from x cross x, satisfying three axioms: positivity axiom, symmetry axiom, and the triangle inequality. Uh, and if this is a metric, then we will just call the tuple xt a metric space. On a space, on a set X, there can be, of course, many different metrics, and each one will be counted a different metric space. First observations are as follows. This is a typical application of triangle inequality. If you have n points like this in a metric space, then the distance between the first and the last one is less than or equal to the sum of the distances between two consecutive terms, x1, x2, x2, x3, and so on. We did this last time, and we also proved this inequality. In a metric space, whenever you have 4 points, x, y, z, w, then you have this inequality. Here you see you have x, w, y, z. They are different elements, and here you have mixed terms, x, y, and z, w. Okay. Okay, we did this last time, and then we gave some examples. First example was, of course, the real number system with absolute value metric. We checked that it satisfies the axioms, and then we considered the standard distance function on the real plane, right? And more generally, of course, this is given on Rn. The standard metric is given like this. We considered this, and we checked the three axioms M1, M2, and M3. For M3, we need to work a little bit, because to show the triangle inequality, you need Cauchy-Schwarz inequality from either advanced calculus or linear algebra. We did this, and what else we did? Okay, we defined three metrics on Rn. Actually, not three metrics, infinity many metrics. D1 was defined like this, and for row larger than 1, D row is defined like this. In particular, when row is 1, of course, you get this. And when you take row to infinity, this metric reduces to this one, taking maximum. So we have three metrics on Rn, and today we will start discussing relations between these three metrics. Okay. Do you have any questions so far on the material? Okay. Okay. Before I discussing the relations between these three metrics, let me make a definition. We will call two metrics okay metrics, let's say D and let's say I shouldn't, okay, D1 and D2, Not necessarily this D1 and D2 on a set X equivalent if there are positive real numbers little m and big M, so these are positive real numbers, so that we have this little m times d 1xy is always less than d2 xy, and this is less than big M times d1 xy for all xy in X. Okay. If we can find two such real numbers, then we call d1 and d2 equivalent metrics. Okay, equivalent metrics. I guess the first thing that comes to your mind when I say equivalent, right? This should be symmetric, right? This should be a symmetric relation here. The rule this equivalence is given doesn't seem like symmetric, right? Here I have d1, but here I have d2. It doesn't look like symmetric, but actually it is symmetric. Actually, being symmetric, let me write as a proposition. Being symmetric is an equivalence relation. Is an equivalence relation on the set of all metrics on X. Okay, so let's see. Okay, first let's see, this is reflexive. So if so we should show that any metric is equal to itself. Well, so just let little m and big M to be 1, then of course m times dxy is just dxy, and this is less than or equal to dxy, and this is less than dxy, which is just big M times dxy. Therefore, dxy is equivalent to dxy to itself, right? Uh, being equivalent, I should say. Thank you. All right. Tamam mı? We defined being equivalent, and we will show that being equivalent is an equivalence relation. All right. Now, let's see whether this is symmetric or not. So, assume D1 and D2 are equivalent. Then, what is the definition? M1 times D1xy is less than D2xy, and this is less than, big M times d1 xy, right? Uh, for some little m and big M, these are positive real numbers, and for all xy. Okay. Well, I should change the role of d1 and d2 in this inequalities. How can I do this? Well, we can do it as follows. You see, from this, the second inequality, we see that 1 over big M1 times d2 uh, xy is less than d1 xy, right? Because just dividing the second inequality by the positive real number m, big M, we get this. And if you look at the second inequality, what you see, d1 is less than 1 over little m d2 xy. So replacing little m and big M by 1 over, by their reciprocals, we get this, right? This is true for all xy in X. Hence, we are done. It is symmetric. For the transitivity, all right, so let d1 and d2 uh, be equivalent, and d2 and d3 be equivalent, d3. So there are constants, little m1, big M1, little m2, and let's say big M2, so that we have this m1 d1. Let me do not write x and y, okay, and then d2 big M1 d1 and m2 d2, and here I have d3, and here I have big M2 d2. Okay. Uh, Wait a minute. Okay. Now I need to have inequality inequalities between d1 and d3. How can we do this? Well, d1 is less than, okay, d1 is less than okay, yeah, m times, all right, let me m1 times m2 times d1. I multiply this one by m2, we get m2 times d2, but m2 times d2 is less than d3, and d3 is less than, you see, d3 is less than 1 over m2 times d2, but d2 is less than big M1 d1, so we get m1 over m2, m1 over m2 d1. So we obtained what? Let's see. Let me just underline the important. M2, D3 is less than M2 D3. Yes, you're right. Okay, so yeah, thank you. This is M2 D2 and yeah, and D2 is less than M1 D1. So I have M1 M2 D3. So now it is more actually symmetric. It's looking better. So M1 times M2 times D1 is less than D3, and this is less than this gadget, right? So we get M1 M2 D1 is less than D3, and this is less than M1 M3 D. Let's have D1 here, right? D2 is less than M1 times D1. Yes. All right. Uh, Hence, D1 and D3 are equivalent. So this proves transitivity. All right. Now, what about our matrix? Now let's see. So what about our matrix? D1, D row, and D infinity. Well, so X is Rn, right? So whenever I have, let's say X is X1, Xn, Y is Y1, Yn, D1 xy was the sum, so x1 minus y1, xn minus yn, and then I have, okay, d2, what was this? This was x1 minus y1 squared, xn minus yn squared, and then you have square root, right? And d infinity, actually we have d row, maybe I write d row xy. This is x1 minus y1 root power xn minus yn root power 1 over rho. Here rho was larger than 1. And we have d infinity xy. What was this? This was the maximum of x1 minus y1 and xn minus yn. I take maximum of these differences, absolute values of the differences. All right, so what is the uh, relations between these inequalities? All right, now let me start with the first one. Last one. Notice that you see d infinity xy. It is the maximum of these numbers, right? Sorry. Whichever is the biggest, we choose just that one. But that maximum is whatever it is. Let's say x I minus or I0, yi0. Okay, one of them is the biggest one, or let me say, okay, kth one. Okay, I write down the biggest one, but this number is less than what? This is less than, of course, the real number, this one, right? Actually, I can write maybe even rho power, and then root, right? Actually, these are equal. I should say these are equal. But this thing is less than what? This thing is less than this one. X1 minus Y1 root power xk minus yk root power and xn minus yn root power to the power 1 over rho, right? Because I have already this term and I have some other positive terms. So clearly this expression is bigger than this one. But what is this? This is just the rho of xy, right? The rho of xy. Okay. All right. What else? Okay. This is less than. All right. Now, yeah, we need to use the following fact here. For D2, this is simple, but okay. This expression here is less than, we apply kind of triangle inequality. So, if I have numbers like this, no, I think this is clear. Yeah, this thing is less than x1 minus y1, and then x2 minus y2. Sorry, xk minus yk, xn minus yn. Why is that? Because you see, maybe it is easier to see this when you have rho equals like an integer, uh, like 2 or n or some integer, okay, m. Why is that? Because you see, when you take root power of this, you get root power of each term, so you get this expression plus mixed terms, and then when you take the root, you will have this terms but plus the mixed terms. Therefore, this expression is larger than this one. So I leave this to you as an exercise. And what else? What is this? Of course, this is just d1 xy. Okay. So what we obtain is then I have and of course, okay, let me write one more step. What is d1 xy? d1 xy is the sum of these terms. This kth term was the biggest, right? So if I replace all the remaining terms with the biggest one, I will get certainly something bigger. So instead of the first term, I write the biggest one. Instead of the biggest one, I write itself, and instead of the nth term, I write the biggest one. But what is this? This is just how many terms do I have? I have n times xk yk, and what is this? This is just d infinity xy. So what we obtain is this. I started with the infinity. The infinity is less than d rho. Oops, d rho. D rho is less than d1, and d1 is less than n times d infinity. Okay, so this means what? D infinity and d rho are equivalent for any rho, right? Hence, d infinity is equivalent to d rho for any rho larger than 1. In particular, right, uh, so d1 and d5 are equivalent because d1 is equivalent to d infinity, d5 is equivalent to d infinity. In particular, d1 and d5 are equivalent, right? Finally, since being equivalent is an equivalence relation, uh, is an equivalence relation, all the rows are equivalent. Okay, rho being uh, positive, okay, is here, or rho is infinite. Okay, these are all equivalent metrics. Well, you may wonder why we defined something like this, equivalent metrics. The reason is the following. Uh, many properties, many properties of metrics doesn't change, or many concepts related to metric spaces doesn't change if you change the metric, if you replace the metric with an equivalent one. Okay, so you may prove, for example, many things for d1, and then we know we will see that all those properties are true for d2 and d3, d5, and so on. Okay, so you don't have to prove something for a specific metric each time. If you prove a property for a specific metric, then that property will hold for all metrics equivalent to that one. That's an important, fact. Do you have any questions? Yes, being a Cauchy sequence, being convergent, we will define open sets, closed sets, and so on. We will see that all these properties are actually doesn't change if you replace your metric with an equivalent one. Okay, we will see concepts like connected metric space, compact metric space, which will be very fundamental for both topology and analysis. And we will see that again those properties doesn't change if you uh, replace your metric with an equivalent one. Actually, hmm, nasıl? Yes. Mm-hmm. Oh, you mean okay? If it is complete with respect to one metric, then it will be complete with respect to all of them. This is what you mean, right? Okay. Yeah, you are right. Okay. Well, before I go to definitions like open set, closed set, we need one more definition, example of a metric. So let's say this is uniform metric. We'll make use of this a lot. So let me define this. Let S be any set, non-empty set. Okay. Non-empty set. A function f from S to real numbers is called bounded if there is some m so that uh, f of s is less than m for all s in s, right? The values of this function doesn't get just too high. All right. Now we define metric on the set of bounded functions. Let Bs be the following set. So this is the set of all functions from S to R such that f is bounded. Okay. Then uh, uh, we define a metric on this ds as follows. Okay. Define a metric on Bs called the uniform metric as follows. So if f and g are bounded functions, we just let the uniform metric. I write usually this sup between, so the distance between f and g is just the supremum of f of s minus g of s, right? These are real valued functions. I can always take this difference and take supremum over s. You see, f and g are bounded functions. F can take at most, let's say, the value 5. G can take at most the value, let's say, 10. The difference can be something between 5 and, I don't know, 0 and 15, I guess, right? And you just take supremum over S. Supremum over S. So this sup is indeed a metric on BS. Okay, I made a, sorry, şöyle yapayım. Okay.